And there are three keynote talk, ECCV'24, and I'm very impressive about the first one. It is the synesthesia. So, do you know what the synesthesia is? Okay, me too. Before going to ECCV, I never heard about this company, but it currently is a unicorn. It means the capital value of this company is greater than $1 billion US. And the left, okay, let me show the, not this one, sorry. She is a professor at University College of London, okay, and you can see she co-founded the Synesthesia in 7 years ago, only 7 years. And she also served as the program chair of CPR16 and ICV'23. So you can see her contribution for the computer vision community is quite significant, so that she can serve as the program chair. And so the keynote was given by both of the two speakers. She is the first speaker, co-founder, and he is the second speaker. He currently is the director of the science at Synesthesia, and he also was the program chair of ECCV'18 and the general chair of ECCV'20. So he is also a very, very prestigious researcher at computer vision. So let's show what is Synesthesia. First, why they established the company in 7 years ago? Because for the first two, okay, the first two is young people are business-based young men. Okay, they had the idea. They found people like to watch real human videos rather than reading documents, word-based documents. So their idea is, could they just use computer to generate videos with realistic human, okay, to replace word-based document. And the following two, they are professors. They are technical-based, okay, and that's the beginning of the company. And this is their product 5 years ago. Let's take a look.
Malaria isn't just any disease. It's the deadliest disease there's ever been.
Se dice que ha matado más de la mitad de la población que ha existido.
وما زالت تقتل طفلا كل دقيقتين.
Mais nous pouvons y mettre fin. Nous savons comment, nous en avons la possibilité.
हमें और अधिक कार्रवाई की जरूरत है.
我们需要让世界领导人关注.
Hivyo tunazindua kampeni ya sauti.
Speak up and say, malaria must die. One voice can be powerful, but all of our voices together, then they will have to listen. Malaria must die, so millions can live.
All right. Now you can see they can speak it in 7 different languages. Why? How did it do? Okay, let's...
Malaria...
okay, this is technical behind. So let's take a look. Okay.
Malaria isn't just any disease. It's the dead...
Sorry.
It's...
What is this? Facial localization. 3D mesh facial localization.
The deadliest disease there's ever been.
You see 9 people there. They are the speakers. The backhand's voice comes from them. Okay.
زالت تقتل طفلا كل دقيقتين.
We're using AI to do what we call visual synthesis. It's actually the same thing as you would do in a
This is the first co-founder. Now he is the CEO of the Synthesia.
Hollywood studio. We use the video to build a 3D model, and we can then reanimate that, so you can change the language or you can rewrite the script of a film. I think machine learning and AI is going to be a very important part of
Sorry. It's weird to control the...
It's going to be a very important part of
You can see this is the technical behind it. They use the computer vision techniques to localize human faces in 3D matches, and this is a segmentation method. They can segment the facial region and other regions. So this is a landmark localization point, and I don't know what the remaining two are. Okay.
solving the world's health problems. What we are doing, I think, helps spread this message in a much more effective way than without using technology like ours.
I've been involved.
Right. Okay, so this is a technical in 2018. So it means given an input image and a target video, they can modify merge the target video's appearance with the 3D tracked actress here. Then merge the two sources of input on the single 3D avatar. And what is the missing part? The missing part is the teeth. So they need to use rendering and games to generate the teeth part. Okay. So here, the output video will have the appearance of the target video, but the pose will be the same as the source video. Okay. And then the technical keep improved. Here, they still use a source video to contain the audio part, and then they use text to speak model, so that users just can type in the sentences they want to speak, and they will automatically generate the voice. Okay, and they can they use the target video. Okay, this is a video, and they can use avatars. They are pre-built in their data set, and just let the users pick up one avatar they want, and then all of them combined, they were using neural rendering to generate images very, very realistic. Okay, this is a technique 4 years ago. Okay, then in 2023, in 2023, after the C round, they kind of unicorn. Okay, and this is their result. Product last year. Okay, and there are some. So there are several generations of product. Currently, the mainstream of their product is version 3. Okay, and what happens? They just released their version 4. Then it press 1 means their voice and their actions are more expressive. Okay. So there's a comparison between version 3 and version 4. So the video is cropped from the video recording of the ECCV website. So let's play it for.
In the same dress, but she's saying the same words, so it's kind of a scientific comparison. That's V3.
Hi there. I am so happy to be here today with you all. I am a digital avatar created by Synthesia. I look and move like a real human, don't I?
And now again in V4 Tech.
Hi there. I am so happy to be here today with you all. I am a digital avatar created by Synthesia. I look and move like a real human, don't I?
Okay, I believe you can sense the difference. So with the technical improvement, this is avatar. This is not a real human. Okay, this is rendered by computer. Okay, but it looks like real human. Okay. And this only version 4.
In the same dress.
They have an ambition for their next generation version 5. So this is a real video taken by the real human. You can see what is I say what is difference between real human and an avatar is real human has a personality, but the avatar currently don't. They want to put or insert the personality into avatars. Okay? And so the avatar can make jokes, will make some mistakes, and will interact with the background, the environment. So that's their goal in the future. So, okay, so what I want to say is, okay, so this is technical direction. What do they want to do? They want do the, compositionality. It means given a voice model, okay, and given the animation model, the voice model and the animation can be combined in a certain way. So this will generate a model. The pose will like the animation model, but the appearance will like another voice model or something else. Okay? And they also have an ambition. They want, okay, not only pick up an avatar from their repository, they can want to use large language models to render the background. For example, given they use language, okay, to, for example, will light room with blind in the background, then they will render the background like this. And even two golden decorative parts like this. And even the appearance, the dressing, and the hairstyles, they want to use multi-language to render it, not rather than just pick some pre-trained or predefined avatars. So how to do it? We don't know, because this is a technical challenge. Okay, maybe some new method or new algorithm will be developed to achieve this task, and they will use those technicals into their products. Okay, so this is their really released product called a personal avatar. So what it means, okay, you can use your cell phone or your cameras to take a video for 5 minutes. Then they can recognize your face, your poses from the videos and become an avatar. So you can use the avatar to do what? To do any commercial or YouTube clips, or you can try to promote your product or services in different languages. They can automatically change your shape of mouth to speak in another language. Okay, and they also can change the background. So you can move, you can should say take your own videos in the class and then show up in somewhere else, on the street or in a garden or something else. Okay. So even you can change your pose. So for example, this one. Now she is sitting on the ground, and you can also change the camera angle and create dialogues. So all of them, the products combines many computer vision techniques into, they apply those I should say state-of-the-art method into their product. And their further future is currently those avatars cannot hold an object because it is difficult to model a hand and then combine it with an object. They want to do it in the future, like this one. I think what is his name? Sorry, I forgot. He is a star, but what is his name? Oh, yeah, Brad Pitt, right. He is holding a cup of some tea, something else. They want to do it in the future, okay? And they also want to, for example, you can tag something in your video, okay? This is their long-term goal to do it, okay? So let me think another problem. Whose jobs are replaced partially? There are many different type of jobs. Okay, there's need of video, so the customers needed the professional video makers to create those videos. Now with the newly developed technique, the synthesis technique, those jobs are partially replaced. Okay, now let's go back to our deep learning slides, right? So what we talked about 2 weeks ago is deep learning means given the input data, the neural network will automatically extract some features and apply the machine learning algorithms to generate the output. Okay, so this is called deep learning. So, okay, I remember in previous week, Professor Albert Ma asked one of you about asked Kenji, right? Kenji Chen. Kenji, you show some face detection algorithm using OpenCV, right? And Professor Ma asked you, is this a deep learning algorithm? No, it's not a deep learning algorithm. The reason is the feature used by the cascade classification is the handcrafted feature. It's not a learned feature from the network. Okay, so it is this part. Okay. And use the machine learning algorithm to do the classification problem, whether it is a face or it is not a face. Okay. All right, so this is the conventional layer by layer neural network architecture. It even go this way or go this way. It is some activations go from the layer 1 to layer 2 to layer 3, etc. Okay, and we introduced batch normalization and stopped 2 weeks ago. So batch normalization is a very currently very widely used technique. It means when we train the network, we not only use an instance per training, we use a batch of instances or training data altogether. And the reason is, if we just use a single instance, usually the gradient is very unpredictable, and the convergence of the optimization will be very slow. So we use a batch of instances together. So, but when we use a batch of instances, the batch normalization method was published in 2014. Okay, before the batch normalization, even we use a batch of instances, the convergence rate is not very good. So the two authors developed the batch normalization. It means given a batch of instances with a certain layer, it normalizes those batches. Normalize means let the output of the batch, their means become 0 and their standard deviation become 1. So here you can see this is the output, the mean of the batch output, and this is the variance of the batch output. They just simplifies the normalize it. Okay, but however, if we use batch normalization, some information will disappear. So they added 2 more parameters, the gamma and the beta, to reconstruct the signals after the batch normalization. Okay, so this the experimental result of the Bayesian narration. Before Bayesian narration, the state-of-the-art classification network is GoogleNet. Okay, so this is the performance of the GoogleNet. Or there's another I should say net for GoogleNet. It's inception. So this is the learning performance of the GoogleNet or inception. It means if we train more than 30 million steps, the accuracy will achieve around 72%. Okay, and when they apply batch normalization, okay, on the same GoogleNet, they can just train the network with around 13 million steps and achieve the same performance. So this is the contribution of the Google. And they also found another things. Okay, since the normal batch normalization can improve the network to converge more quickly, can they change the learning rate? Okay. So yes, so they try if they enlarge the learning rate 5 times, then what will be? So it will be this dashed curve. Yes, it works quite good. It only used 2.1 million steps and achieve the learning rate, and even the learning rate is slightly higher than the original inception network. If they change the learning rate to 30 times, then okay, what will happen? It means it takes more steps and achieve a better performance, 74.8%. Okay, and if they change the activation function from ReLU to sigmoid, what will happen? Okay, the accuracy is slightly reduced. So from this experiment, they show a very convincing result to the research community. But there's another interesting point is, from their title, you can see accelerating deep network training by reducing internal covariance shift. In this paper, they claim the improvement is caused by reducing internal covariance shift. But yes, I know it. Okay. In fact, it's not. But however, the paper is very, very influential. Until now, there are more than 57,000 citations for this method. So it is very, very widely used. So what is the true reason for the effectiveness of the batch narration? In fact, well, from this paper, it is published in NERD-IPS 18, okay, understanding back normalizations. Okay, the authors pointed out the true reason the batch normalization work is because it prevents the large gradients. With less large gradients, the miniaturization operation can go more stably to the local or global minima. Okay. So in this paper, the authors show 2 interesting figures. The first is, with batch normalization, this is a distribution of gradients in the network. So you can see, be careful about the range. This is only 0.04 to negative 0.04. This is a quite narrow range, okay? And without batch normalization, so 0.04 is around here and here. Without batch normalization, there will be a lot of large gradient values. So you can see there are many gradients greater than 2 or less than -2. Okay, so that's the reason. With batch normalization, they change the distribution of the gradient so that the network converged more quickly. All right, so yes.
Why do you normalize only one batch level? Like you take the batch rate, so for example, like 64 images, but like why not 2 batch or 3 batch or half a batch?
Okay, I think are you talking about the size of the batch?
No, like independent of the batch size. Like yeah, like why do you could, for example, like you calculate the mean and the standard deviation based on the batch.
Right.
But you could, for example, like save that and then look at the next batch and then update the previous, using the previous mean from the batch, update it with your new examples, and then your mean would potentially better represent the entire data set rather than if you only use one batch.
Okay. Oh, as far as I know, there are many batch normalizations in a single network. Okay, for example, ResNet. You know, there are many layers, right? ResNet 50, 101, and 152. Okay, for each layer, there is a batch normalization. So there are many batch normalization in a single network. Okay, so does it answer your question?
Not quite. Like I think I'm more interested like in when you go from batch to batch. Each time you do the calculation.
Yes.
From start.
Yeah.
So why not calculate over 2 batches?
What do you mean over 2 batches?
What he means is like 2 batch normalizations after each other directly. Just that.
Sorry?
Like 2 batch normalizations directly after each other.
No? Sorry, my communication is not good. Like instead of like if you have a batch size of 64,
yes.
You calculate the 64.
Yes.
But why don't you calculate across 128? But the batch size is still 64, but you calculate across 2 batches. Because then you have better, your mean is more closely capturing the population mean.
Okay, I'm not totally sure about the Yugo, but I have another perspective. This means in the beginning, the batch means you train multiple sentence instances at the same time. So in the beginning, you need to control the size of the batch. It will when you design your network, you need to you can, so that you cannot change the number of batch size during the network. So I do not fully understand why do you what is the question? You have 140 batches and then you only pick a 40 partial of it to the next layer. Sorry, I don't know. Okay, so no. okay. Okay, so now our authors want to go to another topic called backpropagation. So he first talked about the loss function for classification. For classification, the widely used loss function is the logistic regression. It looks like in this way. And just a slightly change the notation, it will become this. So the TIK means there are several classes, and only one is the correct classes. For all others, they are wrong classes. Let's go back to the ImageNet, for example. There are 1,000 classes, and given the image, then your network will generate 1,000 probabilities. But your label is one among the 1,000 classes. Only one is the TIT here is for a certain classes. For K is 1. For the dog classes, this is 1, and for all other 999 classes, the TIK is 0. So it means the TIK will indicate which probability the log value of probability you will use to calculate the loss function. So that is simplified notation will be the TI will be the correct class label. Okay, so we only need to care about the PI. I means the instance. So it means given for example of the ImageNet, you have more than 117 million instances, so that is I. And within the 1,000 classes, you will only care about the probability of the correct classes, and you neglect all other classes. Okay, and for so this is the definition for multi-class cross entropy for logistic regression. Again, here I should say, let's go back here. Okay, so logistic regression is what? What it is a machine learning algorithm. So here we use the DOS of the logistic regression. And even for neural network means we generate some output value from our network, but we still use the machine learning technique of problem definition. Therefore, here for the neural network our author changed the index of so that it become PNTN. Okay, it changed I to N only. From the definition, the PIK will be this. What is this? This is the softmax function. Okay. So the loss function become okay. Because this is definition of the probability of the PIK. Therefore, based on the definition of the PIK, the loss function for a single instance, okay, it becomes, so let's go back here. This is the definition. The definition of the loss of a single instance is the negative log value of its probability. And the probability is calculated through a softmax function. So the definition of the PIK is here. Therefore, we got this. The loss of an instance is the log of the normalization term minus the output of the network. Okay. So this is the illustration for this process. This is the probability PIA or PIB or PIC because they are generated through a softmax function. And this is the output of the network. So this is the SNTN for this, or for this. Okay. So that is multi-class entropy, cross entropy is used for classification, and for regression, then usually we will use L2 loss. So this will be the expected or target value, and this is the network generated output value. When they are vectors, the L2 norm of the two vectors and their summation will be the loss. So we see classification and see regression. And the third loss function mentioned in our textbook is the contrastive loss. It means we want to learn an embedding from our given vectors. We have some labels to annotate whether the two vectors are similar or dissimilar. If they are similar, their learned embeddings should be close to each other. So this is the distance, Dij, for two embeddings. If they are similar to each other, then their similar loss function should be small, okay? And the label Tij will be 1 for similar or 0 for dissimilar. So for similar vectors, their loss should be grouped by this summation. And for dissimilar vectors, they should be grouped by this summation. So let's see a very, very famous method in recent years. So this is the clip. Clip is very, very interesting and famous. Okay, so first of all, the method was released by OpenAI. I think everybody of you know OpenAI, right? And the first author of this paper, Rafael, who is he? He is the so you know GPT-1, GPT-1, GPT-2, and then we use GPT-3, right? GPT-3 become GPT-3 become ChatGPT, and the Rafael is the first author for GPT-1 and GPT-2. Okay. And his idea, their idea is very straightforward. Given a sentence and given an image, can they learn a mapping or an embedding through a text encoder and the image encoder to connect the data in the two domains, one from image, another from text. So this is why it is called contrastive learning, because for text and image, how do you know they are similar or dissimilar? Yes, it means given a batch of sentences and a batch of data, they learn the embedding feature. If there is a dog, then the dog image feature of the dog and the sentence feature of the dog should be highly close to each other. So that is this. Their distance should be small in the embedding space. Okay, and here they measure the similarity in cosine cosine distance rather than this L2 known distance. So let's take a look of this important paper. Okay, so their pseudocode is very, very short and clear. It means given an image I, and they use some existing image encoder to get the image feature, and given corresponding text T, they also use some existing text encoder to generate the text feature. Then they want to learn a linear transformation, so that the W here are two metrics. They convert the visual feature, image feature, and the text feature to the same dimension. So this means the embedding space. Just use linear transform, very straightforward and simple. And then they compute the logic. It means the similarity of cosine similarity between the two features. It means this metric. Okay. So the logic is that metric, and then they compute the cosine entropy loss. Okay, because here there are two different domains. One is image, another is text. So they want to calculate the cosine, the cross entropy loss for images, so that they need to calculate this row and so this color, and this color separately. If they want to calculate the similarity for the text features, they want to calculate the cross entropy for this row and this row and this row separately. That's the reason where they need to calculate the cross entropys for the two domains. And what is their final loss? It is very simple and straightforward. Just combine them and divide it by 2. So the two domains are importance of the two domains are equivalent. Okay. So when they train when they have a larger data set to train the contrastive learning, if they can succeed, then how to use the learned metrics. Okay, the idea, the usage is also straightforward. Given an image, let's think, what is our task for the classification problem? It means, given an image, we would like to know what the label of the class should be. Is it a bird, dog, car, or a plane? Okay, so what are the labels? They are the CV10 labels. Right? So given image, they use the the image encoder and use their learned metrics. They can generate an embedding feature. And from those texts, they use those labels to create a sentence like a photo of a dog or a photo of a bird. Then use the text encoder and the pre-trained metrics to convert the features into the embedding space. Then they just calculate the cosine similarity from this image feature and those text features to find who is the one with the highest similarity. Then they decide, okay, this is the image of certain classes. So the idea is straightforward, but let's take a look. Why the paper is important? Because they use a very huge data set, 400 million image and text pair. Okay, and interesting, they didn't release the code. Okay? They released the trend weight, but not the data set. Okay, and then for the image text encoder, they just use the state of the transformer. And for the image encoders, they try different encoders. So Resonate 50 and 101, this is widely used. And there is another network called ECCV'24. It is a scalable dataset. It means usually when you use more parameters, when you enlarge the width, height, and the channels of the network, you will get a better performance. So ECCV'24 means that is the papers published from Google. They use the network architecture search method to adjust or to optimize the size of the width, the height, and the depth of the network to get the best performance under a certain threshold of parameters. So, okay, so the symbol here is if they use the parameter as 4 times of Resonate 50, okay, there is a best combination of the width, height, and the number of channels. And then 16 times or 64 times, okay, it means you use 64 times parameters as Resonate 50. Okay, so this also is a very, very huge network. And then there is another image encoder. It means vision transformer. So the vision transformer, this is base. So it is also different scales. The base, the large, or even okay. And the number of 16s is the size of the input patch, 16 by 16, 32 by 32, or even 14 by 14. Okay, so they try different image encoders, and we will see their performance later. And interesting, how large is their batch? 32,000. Very, very large dataset. Okay. And how many times they need to train the dataset? For this, their largest dataset, they need 18 days on a cluster of 592 V100 GPU. Okay, so our next question: how many V100 CPU do we have in our CGU AI center? I remember the number is around 16 or 24. Okay. But they have so OpenAI. So this is the work of OpenAI. They have so many machines to do it. Okay. For a relatively smaller network, VIT large 14, okay, they also need 12 days, okay, to run the 32 epochs. So this is why, okay, let's see their performance. Let's see here, okay. Let's explain what is, you can see here, this is a linear probe. Okay, so do you see a term here, linear probe? What does it mean? It means, you know, I assume most of you know what the ResNet 15 is. It is a network for image classification. Okay, so it means you can use ImageNet. There are 1,000 classes to pre-train the ResNet 15 architecture, and the weight will learn a lot of information from the ImageNet because it's a huge data set. And then, okay, because there are 1,000 classes ImageNet, but for your target task, for example, this is a CV10. CV10 means what? You only have 10 classes in the data set. So how would you transfer the knowledge from ImageNet to CV10? Easy. Just replace the last digit. What is the last digit? Let's go back here. Okay, here you see 3 different scores, right? So for ImageNet, it means you will have 1,000 scores here. But for CV10, you will only have 10. So just replace this layer, reduce the 1,000, and replace it by 10, so that you can do the linear probe. Okay, and sorry, I run out of the time. So okay, let's stop here, and let's keep it next week. Okay.